Wait. Hello, everybody. Okay. Hello. This video, I'm going to talk about how to represent the triangle distributed load by a discontinued functions. Okay. And this triangle load is kind of very special. Okay. This triangle load is not okay. It's right at the middle part of the beam. Okay. For this case, the if you want to represent this kind of triangle load by a discontinuity function, and it is a kind of trick. Okay, so I want to explain this to you. Okay, so let's look at this triangle load. Okay, it's distributed from x equal to 3 to x equal to 9. Okay, and here is 0 and the end is 12 and 12 kilonewton per meter. Okay, we want to express this triangle distributed load by a discontinuity function. Okay, first of all, let us try to calculate the slope of the triangle distributed load. Okay, because we need to know the slope. Okay, the slope is okay. The slope is okay. Don't think it's very diff. Don't think. Don't think in a difficult way. It's actually is delta x and delta y. So okay, the end is 12 and the beginning is 0 and 9 minus 3. So it's equal to okay. So the slope here is 2. Okay, slope is 2. Okay, here m is 2. M is equal to. Okay, so distributed load. In previous section, we said that if you have the linear triangle distributed load, okay, the load is equal to the slope times the discontinuity function and power 1. Okay, so this start from x equal to 3. So the slope is 2. So we may think the distributed load is the Wx is equal to 2 times x minus 3 power 1. Okay. So but that's not the true solution. Okay, this is not equal to this is not true. Okay. This is not true. Okay. Okay, why? Because in the previous section I say this is all the way to the end. All the way to the end. Okay. It's all the way to the end. All the way to the end. Okay, that means this triangle distribute load is like this. Okay, I have to draw the picture. Okay, I'll draw it again here. Okay, let's say it starts equal to 3. Okay, and the end is 12. Okay, so if we draw this one, this means this discontinued function means the all the way to the end. All the way to the end. Oh, sorry. The slope, I make a wrong mistake. Okay, this slope here is 12 kilonewton, but it's pointing down, so it's minus 12. Okay, so it's minus 12, so minus 2 here. Sorry. So it's minus 12. Okay. Okay, so that's a small mistake. Okay, here back to this explanation here. If I write the triangle load as minus 2 times x minus 3 bracket power 1, that means distributed load is like this. Is like this. All the way to the end. All the way to the end. All the way to the end. Okay, so that means this is, so you can see this is not equal. Not equal. Okay, not equal. Okay, so this function, this discontinued function, definitely not the solution of this distributed load. Okay, so what is right expression of this triangle distributed load? Okay, and here we need to make some trick. Okay, the trick is also start from this graph. Okay, so let me adjust the screen a little bit. Okay. Okay, we also start from this graph. Okay, let me draw it again. Okay, or okay. Oh, it's okay. Okay, well, let's start from this again. 0 is maybe this 3 is 12. Okay, okay. This is this discontinuous function. Okay, but our solution is the triangle distributed only exists in 3 to 9. Okay, only exists in 3 to 9. 9 maybe we'll draw 9. Maybe let's say it's here. Okay, so this is the region we want. This is the region we only want. Okay, the red area. This red area is what we want. Okay, okay. So, so if we want to obtain this red right triangle, we need to use the whole black right triangle and minus this trapezoid. There is a trapezoid here. Where's the trapezoid here? I'm sorry. So that means if we want to obtain this the red triangle, we need to use the large black triangle. Large black triangle. Okay, and minus the trapezoid. Okay, the minus the trapezoid. Okay, and then we will get the right answer. Okay, so we already know the blue and sorry the large black triangle here. We already know it. Okay, it's minus 2 x minus 3 power 1. So the rest of the problem is we need to know, okay, what is this trapezoid? Okay, how to use the discontinuity function to represent this trapezoid. Okay, and this trapezoid, okay, we can look at this trapezoid in more detail. Okay, in more detail. Okay, this trapezoid. Okay, we just draw another very graph here. Let's focus on this trapezoid. 9, 12. Okay. So how to use the discontinued function to represent this trapezoid? Okay, this trapezoid. Okay, in this course we encounter the trapezoid a lot. Okay, trapezoid you can decompose it as a rectangular plus a right triangle, right? So we draw a line here. We draw a line here. Okay, we draw a line here. Okay. Okay, and what's the height here? Let's go back to the height is I think it's 12. Okay, so here is 12. So here is 12. So it's 12. Okay, so actually this trapezoid is equal to this trapezoid is equal to a rectangular uniform distributed load. Okay, here it was 9 to 12, 12, and add the this also triangle distributed load, and it's all the way to the end. Okay, all the way to the end, all the way to the end. Okay, the slope here is also -2. The slope is also -2 because the slope does not change. Okay, the slope is also -2. And here the height is 12. height is 12. Okay, so we from the list shape analysis we can know the trapezoid distributed load here is equal to a uniform distributed load plus the a triangle distributed load, and the point and also is another key feature is the 12 is the end. 12 is the end. Okay, in a in the usage of discontinued function, the end is very important, and it's also very convenient. The end we can ignore everything at the end, right? So it's become much easier to use. So the end is very important because it will make life easier. Okay, so the 12 is the end. So the 12 is the end. Okay, so let's back to this. Okay, so okay, let's say, okay, what is distributed load? Represent this distributed by a discontinued function. Okay, actually this is will be equal to minus 12 because it's point down, and it start from x minus 9. Okay, its power is 0 because the uniform distributed load, okay, its power is 0. Okay, and minus x minus 12. Okay, okay, this is this one. Okay, and in previous section, we know that everything at the end can be ignored, so we can ignore this. Okay, so this will be minus 12 times x minus 9 equal and power 0. Okay, okay, so this is the uniform distributed load by a discontinued function here. And okay, so what's the triangle here? Okay, this triangle is start from x equal to 9 and all the way to the end. So I think it's easier to represent by this continuous function. So the slope is also minus 12 and is x minus start from the 9. Okay, and its power is 1 and all the way to the end. Okay, so that's the discontinued function representation for this distributed load. Okay, so so now we can combine all the result together, Okay, okay, so can we circle something here? Okay, can we circle? Sorry, it looks like it's difficult to circle. Looks like this cannot be. Okay, so maybe just put it here. Okay. Okay, so this is small red triangle is the answer we want to know. So okay, so okay, we already know this need to use the larger right triangle here and minus trapezoid. Okay, and the trapezoid is equal to these two discontinued function add together. Okay, so let me write down the answer. It's minus 2x minus 3 power 1 and minus, this is minus 12 x minus 9 0 and plus minus 2, so it's also minus 2 x minus 9 and power 1. Okay, so we can combine all together, so it's minus 2x minus 3 power 1, so it's plus 12 x minus 9 power 0, and it's also power plus 2 x minus 9 and power 1. So I think this is the final answer for the triangle distributed load at the middle part of the beam. Okay, so you can see that, okay, if it's the distributed load, in the middle part of the beam, especially triangle load, you need to use some trick to obtain the answer. Okay, so that's why I record this video. Okay, so okay, simply speaking, you need to do some shape, the subtraction of the shape. Okay, subtraction of shape. Same thing will happen if you have trapezoid distributed load at the middle. Okay, if you have a trapezoid distributed load at the middle, you also need to use the same trick. Okay, so and that would be more difficult, but also maybe that's in your homework. Okay, so I just start a video here. Hope you can get more understanding for how to use how to represent the distributed load by discontinuity functions. Okay, I'll start video here. Okay, see you next. Bye bye.